Hello, welcome you all to the class of data structure. In this session, we are looking at linked list. Linked list is the third module in the VTU syllabus. Before getting into linked list, we shall see what this module comprises of. Linked list definition, then we will see the representation of linked list, in memory, garbage collection, then comes memory allocation, and then operations on linked list. So what all operations you can perform on linked list? Basically, you have to create a linked list. So creation, and then once one node is created, then we have to keep on inserting many more nodes which you are creating eventually. So therefore insertion. Once linked list exists, you have an option for deletion of those nodes. Therefore deletion. We can also implement stacks and queues operations using linked list. So stacks and queues can be implemented using linked list. Okay, then where all you can apply this linked list? In this particular module, we will see these applications of linked list. One is to perform actions on polynomials, maybe polynomial addition, division, any operations using polynomials. If you are performing that, where we are using linked list, and also for sparse matrix. So these are the two applications which will be covered in this particular module. So keeping all this, we have to move with first the definition of linked list. Before even trying to know the definition of linked list, we shall just try to understand the motivation behind the linked list. So coming to the motivation part, to know the motivation of linked list, we have to first realize the limitation of some other data structure. So for the motivation of linked list, we are trying to see the limitation of arrays. What was the limitation of array? Which eventually led to the motivation of linked list. So we will quickly revise the limitations of array. One of the limitation of array was when we requested for 4 elements to be stored in an array, we have understood that all these 4 elements are stored in a contiguous block of memory. That is, suppose if it is starting from the base address of 2000, the next element, since it is 4 bytes consumed, it would be 2004 itself. It could not have any other address. So next would be 2008, next would be 2012. So in this scenario, what happened, when we are trying to consider in a large amount the data, somewhere if I require 4000 block of 4000 elements, if I am in need of, then what is the block size which is required in the memory? So 4000 into 4 bytes. Okay, so with this 16,000 bytes of block were required at a stretch because the memory was contiguous. Okay, so with this, suppose if the memory fails to allocate, memory manager fails to allocate in a stretch the contiguous block of memory, the memory may be available in bits and pieces, but in a contiguous block of memory was not available, then this was the one drawback where memory was contiguous. And because of this contiguous block of memory, the insertion and deletion of an element was very difficult. Suppose if I have to insert an element after 8, and suppose if the memory is available, we have to shift 68 to the next location and 55 to the next location, then make a space and add the element over here, suppose 10. So these were the major two setbacks of arrays, which is leading a motivation for us with the linked list. With the linked list, we will see how we will overcome these two major limitations. Here comes the pictorial representation of linked list. The same values would be stored something like this. These we can call it as a nodes. Since there are 4 elements, I have taken 4 nodes over here. Every node will have a 2 parts in it, where the first part we can call it as a data part, and the next part I can call it as a link part or the address part. Okay, so everywhere, every node will have the data part and the link part. And now the 5 is stored over here in the data part. Okay, every node means it has some memory, and now I will assume this is 3000, this is 5500, this is 2000, this is 1500. Okay, so here with the memory you can understand that the memory is not contiguous. The first drawback setback we have overcome over here, and this is the link part is trying to link to the next node. Therefore logically they are connected, but physically they are not the contiguous block of memory. So this link part will hold the address of the next node, therefore it is 5500, and here the next value is 8, therefore this is 2000. So the next value which we are trying over here is 55, and yes, what is the next address? The next node is pointing for 1500, therefore it is 1500. Here comes the point, the last node which we are coming is with 68. Since this particular node is the last node, therefore the address stored over here is null, which indicates that we have ended with the linked list and there is no more node going ahead to be fetched. Okay, so with this is how the pictorial representation of linked list is seen. Here see the next one which we tried is insertion and deletion was so difficult in the arrays. Here where we can overcome easily. If I want to insert one more node after the 8, I will create a node dynamically, and every node on creation will have 2 parts. One is the data parts and another one is the link part. It is also associated with some memory where we shall assume it is 10,000. Okay, and some value like 10 wants to be inserted over here. So first thing which we will do over here is whatever the address was stored in the node 8, that we will move to this new node, therefore it is 2000. Hence we are connecting this node to here, and now I will reset the value of this particular node to the new node which has been inserted in the middle, and this node address is 10,000. Therefore we are redirecting this particular node to the new node which we are inserting. So this is the simple way of doing an insertion. With this, the insertion and deletion in this fashion will become very easy. That's how we are overcoming the drawbacks of an array, or rather than drawbacks, I would like to say it is a limitations, because limitations itself will always yield for new things to come to that place, or the better things can be performed with the limitations of one particular thing. With this motivation, we have just got to know the overview of how the linked list look. With this pictorial working of that linked list, we shall arrive at the definition of linked list. What is the definition of linked list? Now, linked list is a collection of nodes. It could be 0 node. At the first go, we have started with the 1 node where there were 0 nodes in the linked list. So, linked list is a collection of, this is the definition. So, linked list is a collection of 0 or more nodes, where those nodes are connected logically. So, it is a collection of 0 or more nodes which is connected logically, where every node has two parts in it. One is the data part and another one is the link part. So, every node has two parts. One is the data part and another one is the link part, and the link part will always hold the address of the next node. Link part holds the address of next node. Okay, so this is the definition of linked list, where the last node will hold the address as null, since it is a last node for us. So this is the very simple definition of linked list. With this, we have got the motivation to learn the linked list, and also how is the pictorial representation of linked list is seen, the simple way of insertion. Similarly, we can delete any node. Okay, so going ahead, we shall implement the same things in deep in the memory representation, how it happens with the C language associated. We will try to learn the implementation of linked list. Okay. To start with the representation of linked list, see how the linked list looks here. It has got two parts. Okay, so we need a data structure which can hold two values for us, and also you have to remember over here is both the values are different. 55 is an integer value, whereas 1500 for us is a pointer value. So keeping this in mind, we shall write how to create a memory representation of this. So which is the data structure which is capable of holding more than one value, where all those values can be of different types or the same type? Yes, it is the data structure which can hold more than one value, where all those values could be of different type or same type is a structure. Yes, you are right. So structure node. This node is the name which I am taking for the structure. And now one more thing, I cannot write a simple structure over here because one of the value in this field is a pointer. Pointer of what type? This is not an integer pointer, this is not a floating point variable pointer, whereas this is a pointer which is capable of holding one more node which is of same type. So this leads for you to self-referential structure. So self-referential structure is written in this fashion, where one of the field is integer, and for simplicity we shall represent it as a data field, and one more is link field pointer. I have to write a self-referential structure. How to create a self-referential pointer? Write struct. What is the structure name is node, and then comes the pointer which we are marking it as a link. Okay, so close the structure with semicolon. Here this structure can have any number of fields. Here also data field is much generalized field which we are writing over here. This data field can contain multiple values, like it can have a name, it can have a roll number, it can have address, it can have phone number. Any number of fields you want, you can create in this data field. For simplicity, for understanding purpose, I have taken only one field in the data field, and that is the integer value. Okay. Now with this, I have to create a user defined data structure over here, just because I have to create more and more number of pointers going ahead. Then for readability format, I am creating user defined data type. For that we are taking the help of typedef struct node. So going ahead, I want to create structure type pointers. Therefore here the user defined data type itself I am making it as a pointer and I am writing star node. Okay, so going ahead to create a pointers, I can just use node. This is the memory representation of a particular node. With this line I can create one empty node. For example, to start with, we shall know that right now it is an empty linked list. Right, it's an empty linked list. We have not yet created any node. Now I just have a pointer. How to create a pointer of this structure? So I will create something like this: node star start. For readability format I have taken a pointer called start. Not even star is required because node itself is a pointer for us. Okay, so start is a pointer which is capable of holding a address of something called node like this. Okay, with the help of this start pointer, dynamically we shall create a node. First operation of linked list is creation. Okay, so we are working with creating a node. Okay, so we are trying to creating a node. How to create a node now? This piece of code is to create a new node. Okay, how to create a node? Now node is equal to start. Initially that's a pointer which is not holding any address for us. So I can initialize start is equal to null. Okay, this indicates that now the empty linked list start is null at the first go for us. Now how to create a node? Okay, to create a node I will take another pointer, node temp. Okay, so temp is equal to how to dynamically create a node. Okay, we are taking the help of malloc, and for malloc we have to pass the size of integer if we want an integer, then a float if I want float. Now I require a structure, therefore I shall pass size of a structure. What is the structure? Struct node. I can also use user defined data type over here. Okay, so now you know that malloc is going to return as a pointer of void type, so we have to typecast it. I have to typecast to the structure type itself, therefore I can simply use user defined data type called node. So I am typecasting it to the structure type. So this will help me to create one node. Okay, so the first node has been created over here. Okay, which is of what fashion? Two parts is there in it. One is the data part and another one is the link part. Creation means some memory is allocated, suppose 8000, and 8000 is coming and sitting in temp. So the first node is created over here. Okay, so this is how we create a new node over here. Creation happens with this, and if I want to assign a value for this, okay, temp has been created. Now temp of data which I want to fetch over here. So how to assign a value there? Temp of data is equal to 100. If I want to write, I can write it, and this will go and sit the value here. Okay, data field is 100, and now temp of link is equal to null. Okay, this is the shortcut which I have written. It will have data, it will have link. Okay, right now link field is null. This is how I am accessing. Either I can access in this fashion or I can also access in this fashion. Star temp dot data is equal to 100. Both are same. Okay, it is just OR. Star temp of link is equal to null. This is how the creation happens. We have created a node over here and we have filled the values to that particular node, and right now this node has been pointed by temp. Okay, so if you want this node to point it through start also, we can just check is this, since it is the empty linked list. So I will check over here if start is equal to null. It means that it is an empty list yet, and therefore I will make start is equal to temp. With this what happens? Both the start and the temp, both the pointers are pointing to the same node which is just created now. Now the linked list is not empty, start and temp is pointing to some memory location. Is that fine now? Okay, now we understand that linked list is not empty. I can start inserting the new nodes because already one node is existing with us. Now, since a node is already existing, in a different fashion you can start inserting a node. For example, I can insert a node here. So, next node comes in the front of the existing linked list. Therefore, this is called as front insertion. I can insert a node at the front of the existing linked list. Now, I can also insert the new node over here. So, I can insert a new node at the rear end of the linked list. Therefore, insertion at the rear end. Two types of insertion we have already seen. A new node could be inserted at the front of the existing linked list. Therefore, front insertion. And you can also insert a node either at the rear end. Therefore, it is called as a rear insertion. Or when more than one node is existing, you can insert a new node somewhere in the middle also. Therefore, trying to insert a new node at some particular position. Okay, so three different types of insertions we will be seeing going ahead. Insertion is possible in three different fashions. Either we can do insertion from the front end, or you can do at the rear end, or you can do the insertion at a particular position. Positional insertion. So, three different fashion of insertions we will see. Now, as the same code will exist for creating a new node. Repeating these three lines, node temp, and trying to create a malloc and trying to insert new values to this. Suppose now I am inserting 200 in a similar fashion. Since a new node is created, temp is overwritten with the new address which we fetch it. That is would be 9000. Okay, so with this 9000 value, I am concerned now to insert it at the front. Okay, so temp is having a new location for us with the 9000. So temp is no more pointing to this particular node, temp is pointing over here. Okay, with a new value called 9000. And a node has two paths, as you are already aware. This malloc will allocate us the size of struct, where struct has two paths, one for integer data and another one is for the link part. While it is returning as a node, it will give us a node with the null field filled in it. Okay, and the new value is 200. Now, our duty is to insert it at the front of the existing linked list. For this, we are trying to write a code. At the first go, we had checked if it is a empty list. So, condition 1 is already checked. So, condition it is not empty list. Start is if start is equal to null, then only you will put over here. Now, it is not null. So, the next part which we are writing over here is temp of link field whatever you have used, that is so far it is null. I don't want it to be any more null. What the address it has to hold for us? Yes, you are right. It has to hold all the existing link node address. So, which is 8000. From where do I get 8000 now? 8000 is pointed by a variable called start. So, I will write temp of link is equal to start. So, this one line will do front insertion for us. Okay, going ahead now, I don't want start to point somewhere in the middle of the linked list. Start should always point to the beginning of the linked list. So, how to repoint it? let start be equal to temp. So what does temp is holding right now? Temp is holding 9000. So start will also start pointing to this particular node. Start is overwritten here. So no more start is pointing to this particular node. So we shall quickly try to insert one more node in the similar fashion. First line we will go over here. It will create node temp. Okay, this is done. We are not concerned with this now. Okay. So first node it will come over here. Node equals temp. Temp is equal to malloc, it will create. So this line will help us to create a new node in this fashion. Okay, and this will fetch some new address for us. We shall assume it is 3000. So 3000 is the new address. In this fashion we get a node, and here it is inserting a data for us. Now we will insert some new data, 400. So 400 new data is inserted. Now the link field, it is filling it with null, and it is returning us this particular temp. We come over here and check that is start is equal to null. No, start has got some valid address. That means that already linked list is existing. So we come to this point and make temp of link is equal to start. Temp, this is the temp. No more temp is pointing here. So this is the temp. Temp of link, this is the link field and data field. Temp of link is equal to start. What does start had so far? 9000. So temp of link will become start. We are pointing to the next node then, and now no more I want the start pointer to point somewhere in the linked list. It has to point for the starting node of the linked list. So we are repointing start is equal to temp. Temp is having 3000. That makes start pointer to address for the new beginning of the linked list. This is how you can keep on inserting any number of nodes you want at the front insertion of the. So this is telling us how to do front insertion with the linked list. Is that clear? Any doubts so far? No? Okay, that sounds good. With this, we shall see how to do the rare insertion. So in this similar fashion, when I run these three lines, node temp, temp is pointing to the new memory location. We shall take some address as 7000. So new node is created here now. New node 7000 is created, and the fields are filled over there. Temp of data is equal to some address called 800. Okay, some value called 800. We are filling 800 over here, and the link field has been filled with null. This is fine, but the concern over here is we want to insert it at the end of the linked list. Now for that, we have to traverse this linked list from the starting point to the end point. The starting point of the linked list is pointed by a pointer called start. However, I cannot disturb that pointer because it should still hold for me the beginning of the linked list. So we shall use one more variable which we have used for temp. No, the temp is already utilized for me to create a new node. So temp is now pointing with the new address called 7000. So temp is also no more pointing here to the beginning. So with this, I realize that for traversing I have to use one more pointer. So here is the creation of one more pointer, node current, and I have to make this current pointer to point to the beginning of the linked list. So current is equal to start. So current is also pointing to the starting of the linked list. With this, I shall traverse this current pointer to the end of the linked list. How do I traverse? How do I get to know that we have reached the end of the linked list? It is through realizing that when the node's link part is null, at that point we have reached the end of the linked list. So how do I do the same action through code? While current of link is not equal to null, you have to keep moving ahead. How do I move it? Current is equal to current of link. What is happening? Current is start, current is here, current of link is not equal to null. Is current of link is null? No, it is not equal to null. So I will move current is equal to current of link. So current of link is 9000. Current comes from here to here. Now, is current of link is equal to null? No, current of link is not equal to null. Therefore, current is equal to current of link. Current now from this node to it has moved to this particular node. Here is the current now. Now it is again checking is current of link is not equal to null. Is current of link not equal to null? No. Current of link is now null. So what am I supposed to do now here? Current of link, the new address which I have to place it over here. What is the new address? 7000. So this new address is held by what? Temp variable. You are right. So coming out of this while loop, okay, while loop opens and closes over here. So coming out of this while loop, what the code which we are writing? Current of link. So current of link is equal to new node is there with the temp. So this helped us to insert a new node at the rear end of the linked list. Okay, so this is helping us to perform rear insertion. What we are doing over here? Rear insertion. Quickly repeating for you again. Current is equal to start. I am trying to point a new pointer to the beginning of the linked list. With the help of this code, while current of link is not equal to null, we are traversing the current node to the end of the linked list. Once I get to know this is the end point of the linked list, I will try to insert the new node which we have created to the end of the linked list. This is how the rear insertion is performed. You can repeat any number of times these lines and try to insert how much ever the node you required for. Now, the next type of insertion which we are trying to see is positional insertion. So yes, it is positional insertion. What it is telling for us, suppose it want to insert an element after particular node. Okay, so I shall indicate that okay, 400, after 400 I want to insert. So I will just take the key value, key is equal to 400. So the demand over here is try to insert a new node after the key node which is 400. So new node has to be over here followed by this, then the remaining nodes should continue. Similarly, we will start node is equal to temp. Temp is going to create for you a new node. This line will help you to create a new node. Okay, with this two parts is there, and temp of data is equal to some value which we have not taken over here is 700. Okay, 700 is not there. So 700 and the link part. So data part is filled with 700 and the link part is filled with null. So this line malloc means it is allocating for us some memory. So we shall assume that it is allocating for us a memory called 6000. So temp is pointing to the new location called 6000 with us. Here now coming with, this is the linked list which is existing, which is pointing with the start pointer at the beginning of the linked list. Now here also I need a pointer to traverse, you know, where I want to go. So what I will do is I will take the current as a pointer. Similarly, I will write node current which is equal to start. So I am pointing one more pointer current to the starting of the pointer. Now I am checking, am I reaching this key node over here? Okay. So while current of data is not equal to 400, you can keep moving, sorry, 400 is there in the key. So key, until then you can just move current is equal to current of link. So keep moving. Now for now, fortunately, current of data is equal to key. It is. So this is the point where I have to insert it. I got the point. Before insertion, two things you have to take care of here. One thing is this address, you have reached the node next to which you have to insert a new node. But before inserting, make sure that the address which the current node is holding should not be lost. So this address should be stored here. How to store this? Temp of link will fetch for me this location. This value is accessed through current of link. So what we will do here, Coming out of this while loop, okay, we are trying to write temp of link. Temp of link is equal to current of link. See, now we are not losing this because I will overwrite on this the new address which I have got 6000. So this address will be lost. Before losing it, I have to make sure that this is being used in a place where it has to be. Okay, so this line temp of link here is holding current of link. Current of link is 9000. So this address I have stored. So here this is pointing to this node. So we have set the new path now. Only thing here is we have to override this with the new node's address. New node's address is there in the temp. How to fetch this particular location? It is through current. Here in this scenario the start is also pointing, but somewhere here in the middle if you want to insert start you cannot fetch. That is accessed only through current. Therefore current of link is equal to temp. Okay, so with this current of link temp is having 6000, so we shall write this with 6000. So the link breaks over here and the new link is established to this particular node. So this is how the positional insertion happens. Is that clear? Do you want to insert one more element over here? We can quickly insert. You can just choose where you want to insert. Suppose now after 200 you want to insert a new node. Come from the beginning, there is a temp. Okay, temp is no more pointing over here. When I called node temp node malloc, it is fetching us a new memory location. Okay, somewhere with 2000 is the new address which we have got. Okay, now 2000 is there in the temp which has got two paths. Okay, and now here temp of data is holding a new value called 555. Okay, and the link part is with the null. So these lines are ready. Okay, and the new node is being held in the variable called temp. Now the next task is we have to traverse through the linked list to reach the particular position we require. So key value over here is 200 for us. Okay, now key value is 200. Current is at the beginning of the node. So current of data is not equal to key. Yes, current of data is not 200. So current is equal to current of link. So current will move from here to this node which we inserted. So here is the current for us now. And then current of data is not equal to key. Yes, true. Current of data is not equal to key. It is 700. Key is 200. So repeat these two lines again. Current is equal to current of link. So current of link, current is moving to this address 9000. Current is here now. Again now it is checking is current of data is key. Key is 200. Yes, current of data is 200. So current stops over here. It is not going here. Okay, so current stops us here. So current is now pointing in this location. Okay. So before making modifications, we are taking care that whatever the current node link is there, that is not lost. So current of link is been holded by temp of link. I am writing temp of link is equal to current of link. Current of link is having 8000 and that we have written into temp of link. Therefore, it points like this. Okay, see, current of link has been holded to the temp of link. So the new node already has a direction, set a direction where it has to go. The next node of the new node is already set. Okay, now previous node we have to set the value. So current of link is equal to temp. Okay, so temp new address is having how much? 2000. So here I have to set a value. Therefore this becomes 2000 and here comes the new link address. So current of link is equal to temp. This is how we can do positional insertion. In any place we can insert the new node which you have taken. So with this, three types of insertion, not types, three possible ways of insertion. One is the front insertion, then is the rear insertion and the third one is the positional insertion. In all the types of insertion, two things we will take care of. When the node is empty, when the linked list is empty, the new node which you have created, that itself will become the first node. If the linked list is already existing, we will take the necessary steps and make sure that in particular fashion we are inserting. With this, we are finishing up all the types of insertion which appears for us in the singly linked list. There are at the first go I just told you which are the different types of linked list are there. Here we are working with only singly linked list. Okay. In all the different types of linked list, similar fashion will be followed. Okay, now we shall see how the deletion happens in the linked list. So the next operation which we are looking at is deletion. Here deletion can also be performed in a 3 different fashion. Front deletion, or you can delete from the rear end, or you can also do the positional deletion. During insertion, we consider 2 cases. One is if the linked list is empty, then that becomes the first node, and if the linked list is already existing in particular fashion, we do the insertion. Here where we have to consider 3 different cases. If the linked list is empty, case 1, if the linked list is empty, there is nothing to delete. Okay, and the case 2, if there is only one single node. Okay, if the linked list comprises of single node, then you have to take a special care to make sure that going ahead the linked list is empty, to indicate that the linked list is empty after deleting the single node. And if the linked list is already existing, okay, so if the linked list exists with more than one node, then you have all 3 possible ways to do the deletion, either the front deletion, rear deletion, or the positional deletion. One by one we shall take up now. Front deletion. Okay, with this front deletion, if there exists only one node, okay, with some value, and this would be get pointed by start. Okay, so start is equal to 8000. How do I get to know if it is a single node? Okay, before even going with the single node, any deletion it would be. If the linked list is empty, how do you get to know that linked list is empty? Case 1, we are solving. It is empty. If the linked list is empty, I will get to know if start is equal to null. So I will just check if start is equal to null. So if start is equal to null, you can just say that linked list is empty, there are no nodes for deletion. Okay, we can just print linked list is empty. Okay, so the concern arises when we have at least one node. Okay, when there is one node, no point of asking front deletion, rear deletion, or positional deletion. So for all the types, these cases remain same. We will get to know that is the linked list is empty by just checking start is equal to null. So this case is solved. Case 2, when there is a single node which is existing, then also front deletion or rear deletion concept does not appear. Start is equal to 8000. How do I check that if there is only one single node? Case 2, I will check if start of link is equal to null. So this will tell for me it is a single node. So what shall we do when it is a single node? We just have to delete that particular node. So what is the function to delete a node? I can just free start. So we are just freeing that particular pointer. Coming out of that, you just assign start is equal to null. We are taking care that going ahead when the single node is there and I have deleted that particular node, so going ahead the linked list has become empty. So with this, first 2 cases are already handled. So for the third case, the question comes, is it the front deletion or rear deletion? You got to know. So if the start of link, see when there is only one single linked list, start of link field is equal to null. Yes, free start. Free is the dynamic memory allocation function which is used to delete the node, okay, or delete that particular memory space. So free start will free this particular memory. So start is no more pointing to any location, therefore for that I am assigning start is equal to null. So with this first two cases we have already handled. Now with the third case, when linked list exists with more than one node, we shall see different fashions of deleting. So friend deletion, we will start with the friend deletion now. Okay, with the existing linked list, this friend deletion start is pointing to the first node over here. Just by moving this start from first node to the second node, I will remove this access to this particular first node. But since this memory becomes waste and blocked until the program terminates, it will not be freed. To take care of this concern, I will take one more pointer and make it to point with that pointer and free that particular pointer. So how do we take care? So we shall take one more pointer, okay, node current. Current node is the one node which I want to delete it, okay, node current is equal to start. Now start and current both are pointing to the first node in this scenario. Now just move the start ahead, okay, start is equal to start of link. Now start is no more pointing to this 3000 address, rather start is pointing to the second node. Start of link is 6000, 6000 is here. So start is pointing to this particular node. Now this first node is held by the current. So we shall free this particular node. How to free it? Free current. So this particular node is freed. No more it is able to access. You can also assign current is equal to null. So you can reuse this pointer. Without any concern. Okay. So here this node is removed. Now the linked list which comprised of 6 nodes has become the linked list with only 5 nodes. 1, 2, 3, 4, 5. So we have freed this particular node. Okay. So if you just want to try once more with the same code, node is equal to current start, current is null, I can reuse that pointer now. So current start, current is also pointing over here. Start is equal to start of link is 9000, 9000 address is here. So start comes to the next node, no more start is pointing here, start is here for us. With this free current we are freeing it, so this particular node is deleted. No more it is able to access, current you are assigning the null. So this particular node is deleted. Now the linked list is there with only 4 nodes. Is that okay? Is that okay to all? Cool. So friend deletion is over. We shall try to work with the next type of deletion called rare deletion. Now in the rare deletion, we understand that I have to delete the last node over here. When I delete the last node, I have to make sure that the previous node of that becomes the last node. So how we are recognizing that it is a last node? When the link field of that particular node becomes null, it does not contain any valid address of the next node, then I understand that that particular node is the last node. So with this understanding, I should also make sure that when I delete the last node, the previous node link as a null. So while we are traversing, when I reach the last node, I should also hold the address of the previous node. So with this concern, I shall declare now 2 nodes, 2 pointers over here, which will be eventually pointing to 2 subsequent nodes in the linked list. So node current will obviously start with the start Okay, and for now node previous, which will be pointing for me for null. I have not yet started the journey of the previous pointer. With this we shall start here where I have to reach. Current is already pointing to the starting node of the linked list. So I have to reach the last node. How do I reach? We already know, while current of link is not equal to null. Okay, you have to just move current is equal to current of link. But I cannot just close the while loop moving the current pointer. When I move the current ahead, I should make sure that the previous location is also held by another pointer. So that I am making sure that previous is equal to current. Okay, so after moving I cannot do this. So first I should give my place to the another pointer and then move ahead. So we will just swap these two lines. Wherever the current is, that is been given for previous is equal to current, and then move current ahead. Current is equal to current of link. So just close the while loop. So this is making previous. Previous will be pointed here in the place of current, and current will move ahead current. So till where this fashion happens for us, current of link is not equal to null. Is current of link is null? No, it is not equal to null. So wherever the current is, that position is been given for previous. Okay, and then current moves from current is equal to current of link. So current of link is 8000. Current is here for us. And now is current of link is equal to null? No, it is not equal to null. So current has to move again. Before moving gives the its location for previous and then moves current is equal to current of link. Now see, current of link is equal to null. Yes, current of link is equal to null. So we have come outside the while loop. Come outside the while loop. Okay, this is while closes, while ends, or while is closed over here, while closed. Okay, now coming out of this, what are we supposed to do? Two things I have to make. I have to free this last node. We have to delete it. How to delete it? Free current. Okay, free the current. The start is disturbing us. We shall make it here. So start is pointing to the first node. Okay, so we have freed the current node. It has been freed, and we should also make sure that the previous node is link field is null. So previous of link is null. So we will make previous node is held by prev pointer. So previous of link is equal to null. So this line will delete this particular node, and it will make the link field of this as null. So this is how the deletion happens. Shall we try one more node to delete from the rear end? Okay. So here node current is equal to start. Everything has been reset now. Okay. So current is also pointing to the first node we have. Okay. And now it will check current of link is equal to null. Is current of link is equal to null? No, it is not equal to null. So move the current. Before moving, make sure previous is here. So before current leaves this place, gives that position for previous and moves current is equal to current of link, which is 2000. So current is here now. Okay. Again it will check, is current of link is equal to null? No, it is not equal to null. So it gives its position for previous. So previous is no more here. Okay, so it gives its position for previous and moves current is equal to current of link. So current is here. Okay, now it checks that current of link is equal to null. Yes, current of link is equal to null. So we understand that we have reached the last point. So now I have to come out and perform the action. While is closed, free current. So free current is deleting for us this last node. No more we have an access for the last node. But care should be taken that the previous node's link field is null. So we are making previous of link. So previous node has been held by prev pointer. So previous of link is equal to null. So this field is null. This is how we are doing the deletion from the rear end. So now the linked list has got only 2 nodes. So now we shall see the third type of deletion, that is positional deletion. Here also the concern is, when we try to delete a particular node, we have to make sure that the previous node is redirected with the new node's address. So with this concern, here also I want 2 pointers to be pointing, one for the current node which we have to delete, and then the previous node which has to be linked for the next node's address. So with this, node current will start with the starting node, therefore it is start. One more pointer which I am taking, previous, which will be currently holding the null value. We have to traverse until we get a particular node for delete. How do we get to know? Suppose if key is equal to 200, we will traverse while current is pointing to the starting node. Okay, so traverse current until you reach the particular node, but before moving ahead the current, make sure the current position is given to the one more pointer which will be holding it. Okay, so while current of data is not equal to key. Okay, is not equal to key. What we are supposed to do? You are supposed to move the current from that particular node to the next node. Before moving, make sure that position is given for the another pointer. Therefore, previous is equal to current and current is equal to current of link. Okay, so before moving current, now current of data is not equal to 200, so we move it ahead. Before moving, I will make sure previous is pointing to that particular node and current has moved to the next node. Okay, now check, is current of data is not equal to key? No, the current of data is equal to that particular node which we are supposed to delete. But before deletion, make the necessary arrangements over there. What is that? I have to make sure that the address which is held in the node which you are going to delete, that address is moved to the previous node. So how to fetch this address? It is current of link, should be stored in the previous of link. Yes, you are right. Therefore, previous of link is equal to current of link. So current of link is having 9000. Go and store it in the previous of link. So now the new direction is set. Okay, I am okay to free this particular node. So how to delete this particular node? It's as simple as writing free current, where the memory will be deleted. Okay, so with this we will be deleting this particular node. So this is how we do the positional deletion. Is that okay? So we have seen all the 3 different types of deletion with the singly linked list. One is the front deletion, and then is the rear deletion, and then next is the positional deletion. In all these 3 different types of deletion, you have to work with 3 different cases. One is the linked list is empty, then there is nothing to delete. When we have only one single node, then you have to make sure that the node is deleted and tell them that the linked list is empty. And then in the third case, when the linked list exists with more than one node, we have to work with the different scenarios. Different ways of insertion and deletion is done in the linked list.